Hi, and welcome again to Stranger Than Fiction. In the last video, we looked at particles and what they're really like at the smallest scales, and we found out that they can have some of the same properties that waves have. For one thing, just like waves, particles have a wavelength. But that's really hard to visualize. What does it mean to say that on really small scales a particle's like a wave? Today I want to help you get a picture of how it's possible, and we'll start to see that it's a really important idea to grasp if we want to understand how atoms and molecules really work. Now here's why it seems like an impossible idea that particles are just like waves. When we think of a wave, we usually think of something like this, a sine wave. And one thing that jumps out at you right away about a sine wave is that it stretches on forever. It doesn't have a beginning or an end, and that definitely doesn't seem to be true for particles, which do have an edge. But in the last video, I told you that particles don't actually have a well-defined edge. Instead, particles act as though they fade out at the edges. But even if you buy the idea that particles have fuzzy edges, that's not the same as saying they stretch on forever. Or is it? Well, the wave that describes a particle is called a wave function, and it turns out that the height of a wave function, which we call its amplitude, tells us how likely it is we'd find the particle at any particular point. So, we're more likely to find the particle where the wave function has a high amplitude. The trouble is, sine waves stretch on forever, and the height of the peaks is the same all the way down the wave. So if this sine wave were the wave function of a real particle, like an electron, it would mean that the electron was stretched across a huge area, an infinitely large area actually. And everywhere along the wave we looked, we'd be equally likely to find the electron, because the height of this wave is the same. And this picture of the wave function is where the problem is. We're trying to imagine how a particle could act like a sine wave, and as you can see, that gives us results that are really confusing. And they should be, because particles don't act like sine waves. But waves can have lots of other shapes besides sine waves. So now let's think about a particle like an electron, and instead of a sine wave, let's try to imagine what kind of wave would act like a real particle. Imagine I gave you a box and told you there was a particle in it, and your job was to guess where the particle is. If that's all I told you, you might think the particle's equally likely to be anywhere in the box. So without more information, you couldn't really narrow down where it is. In that case, you'd say the probability of finding the particle is the same everywhere in the box. The wave function for that would just look like a sine wave. It would fill the whole box, and the peaks would have the same amplitude everywhere. But now suppose I told you the particle is most likely to be at one particular place in the box. Let's say it has a 30% chance of being at that spot. And the further away from the spot you get, the less likely it is you'll find the particle. So in that case, you might imagine that the odds of finding the particle tail off the further away you get from the spot. So the probability might look something like this, a bell-shaped curve. And what would the wave function look like? Well, the particle acts like a wave, so imagine combining the bell-shaped curve with a sine wave. If we do that, we get something that looks like this. This is still a wave. It still has peaks and valleys like a normal wave does. And if you measure the distance between one peak and the next, you can see it still has a wavelength just like a sine wave. But because we used a bell-shaped curve to make this new wave, its amplitude is much higher over here, where we said the odds of finding the particle are the highest. This kind of shape is sometimes called a wave pulse or wave packet, because the tallest part is all right here in one package. When a particle is moving through space, we can think of it as a wave packet moving. The place where we see the particle is where the wave packet has its highest amplitude. But what about the ends of the wave out here past the edge of the particle? What happened to the wave out there? Well, remember, we made this wave packet by combining a sine wave and a bell-shaped curve. Now most of the bell-shaped curve is here close to the middle. The tails of the bell-shaped curve get very small very quickly, but they never quite drop off to zero. That means that way out here, the height of the curve is very tiny, but it's still there. And that means that our wave packet still exists out there. Its amplitude is just very, very small. In fact, the wave packet stretches on forever, just like the original sine wave did. So that means that when you get just a short distance away from the center, the wave packet has an amplitude close to zero, and the further away you get, the smaller the amplitude is. But it never quite goes away. The odds of finding the particle in this region are way over 99%, but there's still a tiny, tiny chance that the particle can be outside that area. And that's what I mean when I say that the edges of a particle are blurry and not well defined. What seems to be a solid particle is actually a wave. So if the wave function stretches out forever in every direction, that means the particle can occupy all of that space. Particles seem to occupy only a small area, but there's always a tiny chance, an extremely tiny chance, that we'll suddenly find the particle far away from where we expect it. That makes it really hard to get a simple picture of what a particle looks like. If it's 99.99% likely that we'll find the particle in this area, then most of that time, that's exactly where we'll see it. And we get used to the idea that the particle stays in that one spot forever as long as we don't deliberately move it. But quantum mechanics tells us that the wave function doesn't stop where we see the edge of the particle. Instead, it continues forever, although it's very small. That means that we're extremely unlikely to see the particle way over here, but it's still very remotely possible. That might be the most important and far-reaching idea in quantum mechanics. The fact that particles actually act like waves profoundly affects the way all of matter behaves. And it affects almost every application of technology we've come up with in the last 50 years. It's an idea that's crucial for computers, for nuclear energy, for lasers, for the space program, for medicine, and lots more. It even impacts pop culture in the form of Schrödinger's cat. I'm going to spend a few episodes of this series talking about those applications, and the cat, and how they're all possible because of the fact that particles actually act like waves. But before I stop for today, I want to point out something important. The picture of a wave packet I gave you a little while ago is really oversimplified. A wave packet isn't really just a combination of a sine wave and a bell-shaped curve. Wave packets actually have more complicated shapes than that, and what they look like depends a lot on what the particle is and how it interacts with other things in its environment. If we really want to understand quantum mechanics and use it to invent new technologies and understand things like chemical reactions and lasers and radiation, we need to know what those wave functions actually look like and how they act. So that's what I'll do in the next few episodes. We'll look at real-life examples and figure out what their wave functions really look like. And when we know that, we'll be on our way toward being able to use that information to make new technology. In the meantime, if you haven't seen my earlier videos about quantum mechanics, I hope you'll give them a look too. Thanks for watching.